Hi everyone, I'm Nicole. I'm a PhD student in astronomy at the University of Canterbury here in Christchurch. I study outer solar system objects and I use Python pretty regularly in my day-to-day work. So today I'll be specifically talking about pandas and how I use it to organize the metadata that is associated with the images, the astronomical images I use to study the solar system. So here's the outline for the plan for the next 25, 30 minutes-ish. So first, a bit of a general background on astronomy, the solar system, and trans-Neptunian objects, which are the objects I'm interested in. And then a bit more of a specific overview of my research project, and a more detailed look at how I use pandas and what its useful features are for me in astronomy. And you know, if you're familiar with pandas, hopefully you'll just learn some astronomy. If you're not familiar with pandas, hopefully you'll learn about some of its useful features, and you know, my use case might spark some ideas for you. So what exactly do I look at? So I look at the solar system past Neptune, and it's a pretty new field. So these are just icy rocks that orbit the sun past the orbit of Neptune. They're pretty far out. If you look here, things like this is a zoomed in of where Jupiter is, and what I looked at is way out here. So they're all pretty far out, and it's a pretty new field. The most famous of the trans-Neptunian objects is Pluto, but the second trans-Neptunian object was only discovered in the 90s. So with that, it created a whole new field of study in trans-Neptunian objects. So what is unique about TNOs and why we study it is that it's thought to be the leftover remnants of our solar system. So in the early solar system, everything was much, much closer together. The early sun was formed, and there was a huge planetesimal disk of debris around it. And from there, the planets were formed. And as the planets migrated outwards, it scattered all of this debris and ice and rock and made all the current trans-Neptunian region. As the planets moved forward, moved outward, all these dust and like planetesimals were all moved around, scattered chaotically. And so what's left over is clues to what our early solar system would have been like. And so if we study these objects, we can figure out the early chemistry and also how exactly this dynamical history came about. So studying these objects is sort of clues to our past. So how exactly do we study these trans-Neptunian objects? So this is not specific to TNOs. Most of astronomy is like this. Astronomy is all about how do you decipher the light that comes to us from the skies. So the two main methods are either through spectroscopy or photometry. So spectroscopy is when you take light that comes from a source, and it's broken down into different wavelengths, and then you sort of measure the intensity of the wavelengths across different specific wavelengths. And so dips in intensity or spikes in intensity sort of tell you what the chemical composition of the object you're looking at has. So in this case, it's hydrogen. But then photometry is when you the light isn't split into specific wavelengths. You just look at light in a specific range of wavelengths. So you put a filter on the telescope, and so the camera is only capturing a specific wavelength of light, a range of wavelengths of light. So, for example, if you look at, for example, the G filter, it only captures wavelengths from 400 to 552 nanometers. So you're just looking at a specific bandwidth of light. So in essence, photometry is kind of like a very low resolution form of spectroscopy. And because TNOs are really small and far away, we have to use photometry because spectroscopy is a method that requires a lot of light. So What we do with TNOs is we take images in multiple filters, and the different filters correspond to different wavelength ranges. And because they're going to be different levels of brightness across the different filters, we can subtract the brightness between two filters to get a color, which kind of tells us about the spectral slope. So on the right here, there's a plot of a spectra of a TNO, and so one of the few TNO spectras we have. We have a filter in the B band, which covers 4,000 to 5,000 angstroms, and then if you get take another image of the filter of the object in the R band, which is 5,000 to 7,000, it'll cover this wavelength range. So it's going to be brighter in this filter than this filter. So if you subtract these two numbers, you'll kind of get an idea of what this slope looks like. So that's kind of what color in astronomy means. And so all this is to explain what I'm doing, which is I'm studying TNOs specifically in one wavelength range, which is the U band, which corresponds to the near ultraviolet range, which is around 300 to 400 nanometers. And why I'm doing this is because it's a wavelength range that is very little explored in the solar system, specifically because it's very hard to observe in this range on Earth. Thanks to the atmosphere, we can't really, it scatters a lot of UV light. So the atmosphere protects us from skin cancer, but then also hard for me to observe these objects in the range I care about. So pros and cons. But why we want to study it in a UV, or like at least why I want to study it in the UV, is because things like organic compounds and carbon all have UV signatures. So it's kind of like a waste not to look at this range just because it's hard. So this is where my project comes in, and I take images from this telescope called the Canada-France-Hawai'i telescope, or the CFHT, and it's located on Maunakea in Hawaii. And it took images of TNOs from 2014 to 2019 in the U band. And it's also, so that is the data I'm working with, and it complements data that is taken from another telescope that also looked at the same objects at the same time, but in different filters. So it can do that color measurement that I mentioned earlier. So this is all the science side of things. So now we move on to how I use Pandas to answer some of these questions. So when I started my PhD, my supervisor was like, okay, so here's the data, here's the U-band data, but there were some main questions I had to answer, which is, first of all, how many objects did we actually look at? And second of all, how simultaneous are our images? As in, when the two telescopes were looking at the objects, were they actually looking at them at the same time, or like how offset were they? And these are two pretty simple questions, but we just didn't know when I first started. We just had a bunch of images, and there was no easy answer to these questions. So for the first question, how many unique objects did we actually image? I first have to clarify that observations are not the same as images. So I want to make a list of observations, and that doesn't mean just making a list of what images did we take, like image 5 to 500 are U-band images. Like, that's not helpful for me. What I do want to know is, for example, let's say this is image 5, and there are 3 TNOs in this image. That's 3 separate observations, and that's what I want to catalog. And so basically, we had a list of images, but we weren't sure what objects were in that image, or in these images. Handily, there is the Canadian Astronomy Data Center has this solar system object image search that you can use, where you put in object names and it will just spit out, and like the telescope you're interested in and a range of dates, and it will just spit out all the images where this object was imaged. So it would take a ton of time for me to go through every single object I was interested in, because like on the left is basically the names of all the objects that could have been observed by the U-band survey, and it would have taken a lot of time to put them in individually through this search. So thankfully, I could just query their API. But then, when I did that, you just get this really gross return. So what I had to do, So what I had to do next was to, read that return through using the ASCII reader from AstroPy. So I'll go on a bit of a tangent here and to mention AstroPy, which is a set of Python packages that is designed for astronomy. So it's really great for handling things specific to astronomy, like specific astronomical units, or like astronomy calculations, image handling, et cetera. So a lot of astronomers use AstroPy very frequently. So in this instance, I'm using AstroPy's table reader to read the return from that solar system image search, and then it makes that really gross thing that it spat out into a nice AstroPy table for me. But I don't want to use it, an AstroPy table, I want it to be in a Pandas data frame, because I wanted to be able to slice my data and like filter things. So then I had to convert this table into a data frame. So what I did was set up my data frame on the left, loop through all the rows in that Python, AstroPy table. But I have recently learned that AstroPy has a toPandas function if you have an AstroPy table. So lesson learned, if you want to do any sort of converting from some other table format to Pandas, check if there's a toPandas function. But what I wanted to point out, though, is that the nice thing about Pandas is that when you save individual elements in it, you can save it in very different types of objects. So, like, sure, your regular dictionary can handle strings and floats and whatever, but the Pandas data frame will save things like this format, which is a time format from AstroPy, and it will save it in that object type for me. And that's very important in astronomy because, for instance, I want it in this format, MJD, which is a way astronomers use to display dates. So these are continuous counts of days. So instead of like, you know, your regular date is like 17th of August, 2022. It will be something like 5,760 something. So it's like a number that corresponds to a date, and so that's a lot easier to do calculations. But anyway, Pandas will help me store data in all these different types of object types that I care about. So, so when I did all that and made my Pandas data frame, and now I have it in a nice format with all the list of observations in this nice data frame. So then I can do things like figure out how many observations we made. So with Pandas, the shape function tells you how many rows in your data frame, what are the columns, how many unique objects. All these are all the unique TNOs that were imaged. If you want to count how many there are, you can do n unique. So all sorts of fun things. But the problem with what I just did earlier was that I queried every single U-band image taken from 2014 to 2019, and it is possible that some of these images weren't from the data set I specifically am supposed to look at. Someone else could have looked at a patch of sky that happened to have a TNO in it, and so it would have also shown up here. So then I had to cross-reference this data frame with the list of images that I was given at the start. So this is just a CSV file, and this product ID column is where is the name of each individual image that was taken, and then I had to cross-reference that with this image name in my data frame. So I can very easily do that because you can easily read CSV files with Pandas. So this was converted into a data frame, and then I just looked for all unique images and just cross-referenced that with this column in Pandas, made a new column to set it equal to true so that I can just find where it's true and then list all the count the unique TNOs in that data frame. So then I found out that we have looked at 166 individual TNOs in the U-band. So now I managed to characterize that section of my data. So that was very exciting, because that is a lot of TNOs being looked at in a wavelength region where like 10 have been looked at so far. So on to the next question, which was how simultaneous are our images. As I mentioned earlier, the data I've been looking at is from the Canada, France, Hawai'i telescope, but it was also being looked at, the same objects were also looked at by another telescope called the Gemini North telescope, and it was being looked at in different filters, so G, R, Z, J. And so these two telescopes have to be looking at the same object at the same time in order to get a color from the object. And it's a kind of a janky kind of process because one telescope starts looking at it and then it tells the other telescope, hey, I'm looking at this object, can you please also look at this object at the same time? And it's a very novel way of observing. It's not really been done very often, so we had to figure out how well this actually worked. So we decided it's much easier to visualize this process. And so we wanted to make a visual representation of what actually happened, and also try to figure out how standardized was our observing sequence. So once again, we turn to Pandas, and so this is a data frame of images that were looked at by the second telescope, so Gemini North. And so I had to compare it with my data frame that I made earlier. And so these two data frames have sort of start dates, so start times for these observations, and then also how long these observations were taken. And so I made a function to plot these different images. So Pandas has its own plotting function, but this was a bit more complicated, so I had to separate it out. So what I did was make a smaller data frame from the original data frame of observations from within a year, and then have all the dates from the U-band observations from within a year, and that would be the y-axis of the plot, and then from there have a smaller data frame. So loop through that smaller data frame and sort of pull out the filter used for each observation, and so that it can correspond to a color on the plot, and make a bar the length of the observation exposures. So you repeat that, but with the data frame of images from the second telescope, and then you sort of get a plot like this. But so this is for 2014, and so you have one for every single year that the survey ran for. So how you interpret this is the first bars of every. So these are different days, and these are decimal days. So corresponds to time within a day. And so the bars on the top, the purple ones, are all individual images taken by the CFHT telescope, so the U-band images. And then the bottom ones are the images taken by the second telescope. So what we're looking for is how much do these actually overlap? So, so this was the first year the survey ran, so it had a lot of quirks. It was not very regular. Usually it should look something more like this, but the first couple of nights, things did not really go according to plan, as we saw when we made this plot. So for instance, here, there's like a whole gap that's missing here, and we had to go back to observation logs to find out that, oh, the telescope crashed during this time, so that's why there were no images. For here, the weird thing that happened here was, for some reason, there was no U-band taken here, even though the second telescope was observing at that time. That one, we're still trying to figure out what happened there, but that's fine. Here, again, there's a whole gap here from the second telescope, which we also figured out was because the telescope crashed again. So there's obviously some issues happening with that telescope in 2014. Here, we find an individual U-band observation with no corresponding observations with the second telescope. And what we found out was that this was actually a follow-up observation. So we actually already had simultaneous data on this object previously. So that wasn't really a cause for concern for us. So based on this, and not just 2014, all the other years, we figured out that besides follow-up observations, all our U-band data was actually simultaneous. But we also found out that there were a lot of weird things happening between the sequences of observations happening with the other telescope. So doing that sort of reassured us that things were simultaneous, but it also gave us clues as to what could have been going wrong if our data was weird. So with those two questions answered, I could sort of continue on and do actual astronomy type things like look at my U-band image. So this is a U-band image of one of the TNOs I look at, and yes, you can see it's very dim. It's just a blob, and that's what I study. So yes, in conclusion, Pandas is useful for storing, slicing, displaying data, and with a caveat that I am using a pretty small database, and if you have a larger set of data, you might want to look somewhere else, but for me, this works, and it has the flexibility I want to answer sort of these questions that I've been posing. And also, I hope that you also feel that TNOs are cool, and space is cool, and yeah. Any questions?
Thank you, Nicole. Do we have any questions about TNO or Pandas in general? Yes. Yes, please.
Is there any stuff going out to look at TNOs, like robots?
Oh, yeah, so far there's only been one actual probe that has gone all the way, and it's called New Horizons. We've looked at one TNO. It flew past this TNO called Arakoth maybe 2 or 3 years ago, but I don't think there are any more planned in the future, but hopefully, yeah. There was something called the International Ultraviolet Explorer. I think it's been decommissioned, but I'm not 100% sure. But I think the data from that have mainly been on asteroids. So yeah.
Thank you, Nicole. I think that's what Python always shows, that it's really easy for the data analysis part. It's easy enough even if we don't have a coding background to grasp it and use it in our non-coding environment or other than web development. Thank you, Nicole. I think TNOs are cool and you're cool. So thank you. We will have our next session at 3:20. So thank you.